Hello, AP Calculus students. Mr. Ford here with another homework tutorial. Today we're looking at 715, and we're going to do all the problems. At least, this is how it usually shakes out. As I'm working through these, I decide which ones I actually want to keep and which ones I don't. After a cursory look at them, looks like they all look pretty good. And you know what I like about this is that as we keep doing these assignments, you keep seeing the same old topics, and so we're keeping everything fresh, getting you guys all the way to the home stretch, to the finish line, so that you're the most prepared for that AP Calc test coming down the line. So we are going to see a handful of related rates problems here, particularly on 748 and 749. But we're going to get a lot of good review of the key concepts of calculus also. So let's go ahead and jump right into it. We're going to need to look at 746 first, which is some ridiculous derivatives, but we're going to handle them anyway because they're not too tough to do. Let's start with A, which is giving us, I'm going to write it over here. This is y equals 2 to the 3x squared minus x power plus 6x to the negative 0.4 power. I mean, that's insane, but let's handle it. I'm going to go ahead and write down B and C also, since I'm right here. Y equals 6x times the natural log of negative 3y minus, I wonder if that's a typo, minus x to the 6 squared power. I don't like B. I'm going to be honest with you. I think B is going to be thrown away right away. I'm just looking at it right now. I think B is ridiculous. I'll leave it there for now. We'll see. I'll take the first step, and then I'll decide if it's worth doing or not. And then C is y equals 3/7 cosine of 11 to the 0.2x power. I really don't like these 0.2x exponents, but we'll deal with them anyway. Our job is just to do some derivatives here. So we're going to need to remember all those rules that we know for this problem, but this one is just going to be a couple of power rule problems, honestly. dy dx in this case, well, if we're going to be, oh boy. Oh, man. There are parts of this problem that I like, and there are parts that I don't like. First of all, I don't like, I am going to do this problem with you. I don't think I'm going to assign it, but I'm going to work through this problem. This first problem has 2 to a power. The derivative of 2 to a power is the natural log of 2 times 2 to that power. But you need to remember to then multiply by the derivative of the inside function, which in this case is 3x squared minus x. So we're going to multiply that times 6x minus 1. I am here to inform you right now that the derivative of 2 to the x is not on the AP Calc AB test anymore. But derivative of 2 to the x, let's just review really quick. If y equals a to the x power, then dy dx is the natural log of a times a to the x. That won't be on the AP Calc test, but you might have a calc professor that does expect you to know it, so I don't know. There's value in doing this, I suppose. The second problem is much easier because it's just a power rule. It does require us to know what 6 times 0.4 is. Negative 2.4. So it's minus 2.4x to the negative 1.4th power. I don't like that at all, but that's what it is. There you go. That's all the parts to this problem. I tried to color code all the different things that are happening there, but that's it. It's one stepper. Question B is going to require the, first of all, that's not a typo. That's a y mixed in with our problems, which means we're going to get an implicit derivative for this question. Not only that, but this chunk of the problem here was going to require the product rule, since it is two things multiplied together. So let's just try it. Let's see what we get after the first step. dy dx equals, okay. The first thing is 6x times the derivative of the second thing. The derivative of the natural log of negative 3y is 1 over negative 3y times negative 3. The derivative of natural log of x is 1 over x. We have to multiply by the derivative of negative 3y since it's the inside function there. That's where the negative 3 comes from. And we also have to multiply by dy dx since we are differentiating with respect to x, not y. The last part is pretty simple. 6 squared is 36. I don't know why they wrote it that way. How about minus 36x to the 35th power? I don't know why they wrote it that way. It's so stupid. Ugh. Well, let's clean this up. It's actually not too terrible. The 3's cancel out. And this is going to be 6x over y times dy dx minus 36x to the 35th power. And this all equals dy dx, which I think is actually important because when it comes to actually solving this, we're going to want to combine all our dy dx's on one side. Oh, shoot. You know what, guys? Shoot, I'm sorry. I only got halfway done with my product rule. Crap. Boo. I forgot about the second half of the product rule up here. We already did the original first, 6x times the derivative second. Now we got to do the derivative of the first, which is 6 times the original second, natural log negative 3y. There we go. Now it's better. Minus 36x to the 35th power. So cleaning it all up, we got 6x over y dy dx plus 6 natural log of negative 3y minus 36x to the 35th. Let's gather all the dy dx's on the left side. We'll have 1 dy dx minus 6xy, 6x over y times dy dx. And that's going to equal 6 natural log negative 3y minus 36x to the 35th power. And let's go ahead and factor our dy dx out. 1 minus 6x over y. Equals 6 natural log of negative 3y minus 36x to the 35th power. You know, there's probably better ways to write this final answer, but this is what it is. You're going to have 6 natural log negative 3y minus 36x to the 35th power all over 1 minus 6x over y. I'm sure there's a better way to make that happen. You could probably do a lot of work with that 1 minus 6x over y part, but I'm over this problem. Question C is probably the only question that I actually kind of like in this set, so I'm not going to assign this. So you could, in theory, skip the first 8 minutes of this video. Anyway, dy dx here. We can ignore the 3/7 since it's just a constant being multiplied. The derivative of cosine is negative sine of the original inside, 11 times the 0.2x power. And the derivative of 11 to the 0.2x power, remember that is a to the x, not x to some power, so we need the logarithmic derivative there. It's going to be the natural log of 11 times 11 to the 0.2x power. And this is all just multiplied together, so we can simplify as much as we want to. How about negative 3 sine of 11 to the 0.2x power times the natural log of 11 times 11 to the 0.2x power all over 7. How about that? That is not at all what the book's answer says. And now I'm wondering where that 35 came from for those guys. Oh, there's a 0.2. Oh, one more thing. Yeah, there's a 1/5 there. There's a 0.2 hanging out up there. I forgot about that. One more chain rule. We got to multiply by 0.2 here, which I like to think about as multiplying by 1/5, because 0.2 and 1/5 are the same. So it's the same answer. It's just got a 35 on the bottom of that fraction. Wow, this problem set sucks. This is much. I mean, these are legit derivatives to do, but I mean, they're legit in the fact that, like, hey, students need to have endurance and they need to focus on tough problems. And I mean, like, you can do them. I just don't know if there's value in doing them as an AP Calc AB student, you know? I don't know where the problem stops being challenging and starts just being hard for the sake of being hard. It's a question I consider a lot when I'm thinking about math problems to assign. So, I don't know. You know, for the sake of time, I'm probably not going to assign these problems. We'll see. 747, we're going to integrate these. Now, I like these problems. I like these a lot more. They're setting up for the next topic for next week, which is U substitution. And honestly, these are derivatives that would require U substitution that you can do right now. We don't necessarily need to introduce a bunch of terminology and symbols to do U substitution. You can practice the skills needed for it as we are setting things up right now. Let me find those problems again, because my thing just pooped out. Here we are. Now this first problem, 10 to the pi minus 1 dx. This is a constant. Do not be fooled by that. That is not a variable at all. That's just a number. So its antiderivative is 10 to the pi minus 1 x plus c. That is all you really need to do in that problem. Stick an x on it because 10 to the pi minus 1 is just a number. It's not a variable at all. Now, this one, though, is, if we think about how we usually do, let's think about how we usually handle. Now, that is the kind of this is, we're thinking in the realm of a to the x. The derivative of that is natural log of a times a to the x. So we need to think about this. If we took the derivative of 9 to the t minus 1 power, let's just think about that. The derivative of 9 to the t minus 1 power would become the natural log of 9 times 9 to the t minus 1 power. That would be it. Now, so what we need here, we just need this part in our, because that's what's left in our derivative. So we're trying to find an antiderivative. So this guy is almost, that black 9 to the t minus 1 is almost correct. The problem is that when we take the derivative, it's going to produce this natural log of 9 piece. We need that to go away too. So here's how we're going to handle that. We're going to make it 9 to the t minus 1, and we're going to divide it by the natural log of 9 plus c. This way, we kind of lay a trap. Natural log of 9 is at the bottom of the fraction, and it's going to cancel out and leave us with what we want there. So this is the antiderivative that we need for that problem. And for question C, kind of the same thing. I know that the derivative of the sine, I'm thinking already that the derivative of sine of 4m minus 3 plus c is a good answer for this question. I'm already thinking about it. But if we take the derivative right now, let's think about that. Take the derivative of sine of 4m minus 3. You will get cosine of 4m minus 3. That's it. But you are going to need to multiply by 4 because the derivative of the inside chunk is there. So in our antiderivative up here, we need to lay a trap. We need to let that 4 fall into a trap. So let's divide this whole thing by 4. And that will do the trick, because if we divide it all by 4, now these 4's cancel out, and we have exactly what we want, just the cosine of 4m minus 3. So this whole idea of laying a trap in the antiderivative, that's the most important piece. This is your antiderivative right up here. Okay, let's think about some related rates problems here. We have an alien using a mysterious power to make crop circles in Nebraska. If the radius of the crop circle increases at a rate of 6 feet per minute, we want to calculate the rate at which the circle's area is increasing when the radius is 150 feet. This is the problem I've been waiting for in my life, because this is a really straightforward related rates problem. 748. Let's start by drawing a circle, because that's what's going on here. We have a crop circle, and with a crop circle we have a radius, and we have a circumference, we have an area, and all this stuff. But we are told in this problem, we know that the radius of the crop circle is increasing at a rate of 6 feet per minute. So dr dt is increasing at 6 feet per minute. And we are told that in this problem. And we want to know, they even told us that, we want to know the rate at which the circle's area is increasing. We want dA dt when when r is equal to 150. That's beautiful. We like that. I like this kind of related rates problem because it's really straightforward. This is really indicative of what you might see on your AP Calc test, honestly. Now, if you draw a picture of that circle there, you already know that the area is equal to pi times the radius squared. This would be our original equation for this problem. What we need now is a rate equation. We need a derivative, because we want to talk about related rates. So our related rates equation would be dA dt equals 2 pi r times dr dt. And, we talked about this last time. We talked about it in class yesterday. It should kind of make sense if you really understand the derivative concept. It should kind of make sense that the derivative of the area is the circumference. Because if the area is growing, every time it grows a tiny little bit, all you're doing is adding a circumference. One more ring to the circle. And that's what makes it grow a little bit each time. It's pretty cool. For us, we just got to plug in some numbers for this problem. We know that the radius in our snapshot is 150. We also know that dr dt is 6. So this is just going to be, let's see, 2 times 150 is 300. 300 times 6 is 1,800. This is 1,800 pi feet squared per minute. That is the rate at which the radius area of the circle is changing in this problem. That is a really good related rates example. It's really straightforward, really quick, easy to do. That's a really simple problem. I like this problem a lot. 749 is also a related rates problem. It's going to require a little more work because there's a couple different situations to consider here. As Khalid inflates a spherical balloon, Kareem wonders about its different rates. He knows that the rate at which Khalid blows is equal to the rate at which the volume changes, so dV dt. As the balloon inflates, other aspects are changing as well, such as the radius and the surface area. So yeah, we have a sphere that's increasing in size, its radius is increasing, its surface area is increasing, and they're all related to each other. If one of them changes, the other ones also have to change. So that's what we're really doing in calculus, is the study of that change. So the first question, question A, is if dV dt is 10 cubic centimeters per second, we want the rate of change of the radius, dr dt, when r is 3. So let's find some space to work with. If you got a notebook somewhere, wherever you are, let's find some room. We're going to need some thinking room here. This problem is going to require a lot because we got a couple other things to think about here. But the picture will apply to all aspects of it. It's a sphere, which I always draw by drawing a circle and then making kind of a waistband around it like this, and then putting a dotted line in the back like that. It's a sphere. The sphere has a center point, and then it has a radius, and that's the same radius all over the place. That's that. Now for question A, we know that dV dt is equal to 10 cubic centimeters per second. Oh, don't crap on me now, yeah. Per second. And we want to know, I gotta scroll back over here. We want dr dt when r is 3. We want dr dt when r is 3. And that's what we're looking for. So what we need is an equation that's going to relate together the volume and the radius. And the good news is there's a really easy one. The volume of a sphere is, I got to think about it, it's 4/3 pi r cubed. That is the volume of the sphere. That's the original equation, but we are going to require the rate equation. So let's do the derivative. How about dV dt equals, check this out, the 3 actually comes down and cancels out the 1/3, and you get 4 pi r squared, dr dt. And you know what? This is, again, I'm going to take a minute to talk about it, but the derivative of volume is surface area. Because if you think about when the volume changes by just one little tiny click, all you're doing is adding one layer of surface area to the outside of the sphere. So the rate of change of the volume is actually just the surface area. Every time the volume grows a little bit, you're just expanding the surface area a little bit. Pretty cool. Now all we need to do here is plug the information that we know. dV dt in this problem is 4 pi times the radius, which we know to be 3 squared because they told us. And we know that we want dr dt. Oh, you know what? Shoot, we know dV dt is 10. So we actually kind of got to work backwards a little bit on this problem. This is 10 equals that. And we want to find dr dt. So all we have to do now is focus on a little bit of algebra here. 10 is equal to 3 squared is 9. This is 36 pi dr dt. And so dr dt is equal to 10 divided by 36 pi. Or if you want to divide those both by 2, that would be 5 18ths. 5 over 18 pi. Like that. If you want the actual decimal, you could do that. But in general, if this was a free response question, I would not give the decimal. But it is 0.088. And this is cubic centimeter. Or sorry, no, centimeters. It's a radius, so it's just centimeters. There you go. Let's look at B also while we're here. B is going to tell us the same. Well, again, we know dV dt, different number, it's 12. This time we want the rate of change of the surface area when r is 5. So that might be a little more tricky to get. Let's think about that for a minute. This is for part B. Part B. Same picture, but for part B, we're going to be told that dV dt is equal to 12 centimeters cubed per second, and we want ds dt. We want the change in the surface area when, was it the radius is 5? When the radius is 5 centimeters. So this is going to be very similar, but what we need is we need a way to connect together volume and surface area in this problem. We'll need ds dt. Let me think here. ds dt. Well, I know a couple formulas. I know that the volume of a sphere is 4/3 pi r cubed. But I also know that the surface area of a sphere is 4 pi r squared. These are the two formulas that we're going to need. If we want ds dt, though, we're going to need... Interesting. Ooh, okay, cool. So what I'm thinking here is if I take the derivative of the surface area, ds dt, that's going to be 8 pi r dr dt. And that's great and all, except for I don't know what dr dt is. However, I could figure it out by using the volume formula. So this is what I'm thinking. Let's use the same process we used up in part A to figure out what dr dt is, because we know that dv dt is 12. So we can plug that in right there. And we also know that this is when the radius is 5, so we can plug that in right there. We can solve for dr dt. Once we've done that, we can go back over to the ds dt equation and figure that out. I think that's what we're going to do. Let's try that. So it'll be 12 equals 4 pi times 5 squared equals dr dt. I'm not going to use the calculator for most of this problem either, because there's a good chance that a lot of pi's will cancel out if we do this. I believe the answer is a pretty solid decimal, like something we wouldn't need a calculator for. Over here, we're going to get, let's see, 5 squared is 25. 25 times 4 is 100 pi dr dt. And so dr dt in this problem is 12 over 100 pi. And I suppose you could knock that down to 6 over 50. Those are both still even numbers. And so how about 3 over 25 pi? There we go. This is centimeters per second. I like that. I like that because when I plug it in for r up here, or dr dt, when we plug that in right there, the pi's will actually cancel out. Oh, that'll be nice. Oh, it'll be delicious. Let's do it. So now we know that ds dt up here is 8 times pi times the same 5. Radius is still 5. Times our fun answer from earlier, 3 over 25 pi. Right away, we can ignore the pi's. They're going to cancel out. And a lot of other things will cancel out, too. The 5's can not cancel out all the way, but they can balance out. 8 times 3 is 24, and 25 divided by 5 is 5. That's it, 24 over 5. I like this answer, ds dt. I like this answer. You could divide that. It's 4.8 centimeters squared per second if you want that also. Make sure you have the units on it for this, especially if it's a free response question. Pretty groovy. That problem required a little bit of ingenuity. You had to kind of think about how you can get to the variable that you want. Very physics that way. Very physics, yeah. Okay, let's keep going. Question C on this problem is one we're just going to talk about for a minute. Describe what's happening when the balloon if dv dt is negative. Oh, it's deflating. That's it. The balloon is getting smaller. I'm gonna go ahead and stop this video now because my second hour is about done. We will probably do both of the remaining problems, 50, 51. I don't know 52. Is there 52 on the next page? Yeah, I don't know. I don't like 52 very much. I like 51 though. I'll make another video at lunch for 50 and 51. I got to upload yesterday's video, too. I haven't done that. Hey, thanks for making it this far. I am not going to assign the first problem. Lesson learned, 746. these are trash derivatives. We will not be doing those. So even though they are worth looking at in this problem, again, you could have the conversation of what's a problem that's worth doing for you guys, for your time, you know? So anyway, I have been Mr. Ford. I hope you guys have a fantastic day. And I'll see you in the next video where we'll continue and do 50 and 51. And I'll see you then.